Yeah, if you don't mind, Ethan, I'll go ahead and turn things over to you and just welcome people to the Monday seminar series. I assume most of you have been here before. This is a seminar series that was born out of the pandemic and has existed because it turned out to be a lot of fun to meet on Mondays and hear some things related to earthquake physics and machine learning and the application of laboratory data, in particular to tectonic faults. So our normal mode of operation is to ask people to mute, but Ethan Conrad, who's you're going to beat now if you don't know, has offered to speak with us today, and he's also agreed to just have people unmute and interrupt with points of clarification along the way. We'll have a half an hour's worth of discussion and question and answer period at the end, so there'll be plenty of time for questions at the end. And in fact, I'd just like to invite everybody to really think about that. We've all given talks on Zoom before, and we've all experienced that slightly, let's say, hollow feeling of talking to your screen for a while. And so one of the upsides is that it's possible to have a nice discussion afterward, because people can come and go if they can. We don't have to end the thing 5 minutes after the talk. So please prepare yourself to get involved in the discussion afterward. I don't think I have anything else to say. I want to welcome Ethan and yeah, turn the floor over to him. Thank you, Ethan.
Thanks, Chris. Yeah, thanks all for having me and having me for this seminar. So a little bit more about myself. Like Chris said, I'm a PhD candidate here at UT. I'm finishing up now, and most of my work is really focused on structural geology and tectonics, more at the origin scale. And we started thinking about sandbox experiments, and then from there, earth analog materials. And working with Nicola, we started using plexiglass, and then things sort of kind of got out of hand, and it went and blossomed into this project on using plexiglass to try to understand the earthquake cycle. So that has been really cool. I'm really happy to present these experiments and the energy controlled machine. So the title of this talk is Rotary Shear Experiments on an Energy Controlled Apparatus, Fault Weakening, Strengthening, and Acoustic Emissions. This work was done in conjunction with obviously Nicola, but also Brett Carpenter at OU and Giulio Di Toro. Okay. So here we see the E-core, as we call it, the energy controlled rotary apparatus. It's fairly simple, it's small, it's compact, less than 1 meter wide on both sides. And at the top you see we load the E-core with simple gym weights on a dead weight holder, and this load is distributed through these 4 columns to a load cell. Let me just get a pointer here. Okay, that's okay. We'll just use this. I don't usually use a pointer. Here we go. Okay, yeah. So that's distributed through these columns to the load cell and across the interface. And I'll first by describing some of these, like the instrumentation, kind of at this zoomed out view, and then we'll zoom into the sample assembly and look at the sensors that we have mounted around there and that we use to record the mechanical data as experiments evolve. So we're using polymethyl methacrylate or plexiglass, and I'll describe that a little bit more in the next few slides. But we illuminate that with the red laser so we can see what's happening on the slip interface as the experiment's going on. And we record that with a high-speed camera. That camera is recording at about 960 frames per second. To kind of frame that, like a really high-quality video would be something like 60 frames per second. So we have a bunch of frames, and we can really look at how the interface is evolving on the millisecond scale. So it allows us to do many things. And the more kind of new approach to rotary shear that we're doing here is we're implementing a clock spring between the motor and the sample assembly. And we'll discuss that more. And I'll talk about what that does for us and how that allows us to learn some things about the strength of the interface and the earthquake cycle. So here we have the sample assembly. It's numbered here, and I'll just run through it. So we have a load cell and a torque cell. We have 3 AE sensors. 2 are mounted to the side. of the sample assembly here. And then we have a third acoustic emission sensor mounted to the side of the machine. And we've calibrated their voltages to try to pick up like kind of different interesting aspects of an earthquake event or pre-seismic acoustic emissions, these kind of things. We have a vertical displacement sensor, a rotational potentiometer to measure displacement, and then there's this pulley system that sort of communicates the displacement to those potentiometers so that we can get some good measurements. Like I said, the kind of novel part of this machine is implementing a clock spring between the motor and the sample assembly. And we'll get into that more, but just to introduce you, prime you for these experiments, here's just an example of some stick slip events happening for an experiment with PMMA. This inset is showing time versus friction, which we're defining as the shear stress over the normal stress. And we see these sudden drops in the strength of the interface, the kind of stick slip behavior of the interface. And to get into our discussion, or just to kind of introduce the energy controlled approach, I'd like to start with this classic simple diagram from the textbook Mechanics of Earthquakes and Faulting. So like I said, we define the friction coefficient as the shear force over the normal force, and we're starting with the simple block slider. So that pulling force is transmitted to the block through a spring with a specific stiffness, or K. And we find that unstable slip occurs when the change in force with displacement is faster or steeper than the slope of the spring coefficient, right? And that's this point B to C here. And then at C, you start to slow down and then eventually arrest. And this framework has been used to understand friction and applied to friction experiments for decades. And in many of the friction experiments as of yet, the K, or the stiffness, is the stiffness of the apparatus and the material. And this is all well and good, and we've learned many things about friction from these types of experiments. But as you can see, what happens is that we apply a constant, we sort of decide what the velocity is going to be. And so we see the increase in the friction coefficient here, and then you'll see this is one of these experiments from these apparatus that use this approach. You see this sudden drop in the friction coefficient, the slip, but the velocity is constant across there. And in a sense, the lab quake is controlled by the experimenter in this way, and the velocity is controlled by the experimenter. So these experiments are coming from one of Nicola's work in 2012 using this hydraulic axial torsion machine. Now, what we do is we have implemented a clock spring. And by implementing the clock spring, now K is the stiffness of the spring, and we've increased the compliance of the system. And in this way, the slip is controlled by the strength of the interface, and lab quakes occur spontaneously and indefinitely. And we're going to argue that this depends on the feedback between the energy flux, or rate of energy flow over the interface area, and the rate of energy dissipation by frictional mechanisms. So those are going to be controlling the slip behavior co-seismically. And to put these side by side and look at these side by side, we can see some things that I was talking about. So with the classic rotary approach, against the slip velocity is sort of imposed. You have a quote unquote imposed earthquake. Whereas in this case, we have the clock spring implemented, and we gain much more information on the precursory behavior as well as the co-seismic behavior, and as far as the slip velocity. And so why do we call this energy controlled? So this schematic is showing just a simple drawing of our machine with the things that we measure. And the energy flux, which is provided by the spring, is the change in the spring potential area, the change in the spring potential energy divided by the area. So this is in watts per meter squared. And in this way, alpha here, which is the difference in the motor displacement and the sample displacement, is going to increase when the spring is loading. So if the interface is locked, the sample is not moving, but the motor is moving, the spring is coiling. And so alpha is going to increase, and you're going to be storing energy. Now, when you have slip, alpha is going to decrease, and you're going to be releasing energy. And so by controlling the loading rate, we're controlling the rate at which this alpha changes and the rate in which the energy flux is provided to the interface. Now, power density, this is just in terms of terminology, it's also energy flux, but we're calling it power density here, is that which is frictionally dissipated on the interface. And it's MV, or the torque times the velocity, again in watts per meter squared. And that's going to be interacting in this feedback with the energy provided by the spring to control the slip. And then we gain, based on this approach, much information about the earthquake cycle because of this feedback controlling slip rather than it being imposed. And then adding this to rotary shear, we can have infinite stick slip events. So we can keep these experiments going forever. And this is just an example of some data from our experiments with PMMA, where we see how the slip behavior is changing as a function of some changing boundary conditions, and then evolving as a response to that changed boundary condition. And we can explore many different things, and we'll get into these data and this specific experiment much more in the next few slides. But first, just to kind of introduce what we're going to talk about, we can do many
Ethan, can I?
Sure, yeah.
Can I ask a question? I think I might be confused, but maybe. So what you're describing, the energy dissipation, it's exactly the same as what you would have in a spring block slider. So
Exactly.
This is normal for a spring block slider, and it's new for rotary shear. Is that?
So yeah, that's a good point. So in a normal rotary shear machine, you still have it still has a specific stiffness, except you don't change that stiffness by sort of switching out the spring. And then the energy flux, that the machine is much stiffer than our spring. So the energy flux is going to be much higher than you would have when you have an increased compliance. And so because you kind of increase the compliance of the machine and you control that energy flux, you allow the interface to sort of have more control over the slip velocity, and you don't set that slip velocity. It's just responding to the loading of the spring.
Okay, yeah, I think. Thanks.
No problem. Yeah, thanks.
Sorry to interrupt.
Yeah, so I'm going to divide this talk into sort of two parts, two different applications of the E-core. So the first part would be the role of frictional melt, and then later as it cooled pseudotactylite on the strength of the fault interface across its sort of lifetime. So how does the fault interface evolve? How does the strength of the interface evolve after multiple stick slip cycles? And how does the interface change and respond to changing loading rates and those kind of things? And then we'll talk about coseismic strengthening and weakening and monitoring this through the slip velocity, energy fluxes, and thinking about the relationship with the acoustic emissions that are emitted during the events, and how the E-core and the energy control approach provides a benefit to doing these types of analyses. So to get into the first case, so we're talking about, again, the role of frictional melt and later pseudotactylite on the strength of the interface. So pseudotactylite or melt formation is an extreme case of frictional heat dissipation. So this is where you have a lot of energy supplied to the fault, and that energy is dissipated by breaking down the material and melting the material. And this figure on the top shows natural pseudotactylite, and then an illustration of where you might have these pseudotactylites deposited along the fault. So it might be injected into veins, it might be along the fault as well. This photomicrograph from Scambaluri below is showing really nicely the complexity of these vein structures and what pseudotactylite actually looks like in nature. And it's been a matter of debate for the past decades whether or not faults can get hot enough, or whether this is actually melt or microcrystalline material, or what that actually is. So it's been shown, and coming from this Carlson-Jaeger equation, that the temperature can well exceed the melting temperature of granite, for example, during a slip event. And then temperatures in experiments using granite are recorded up to 1400 degrees Celsius. So this is an example from some work from Spray 2005, where they conducted rotary shear experiments on westerly granite, and then they had a pyrometer mounted to the sample assembly, and they were able to measure temperatures well above the melting temperature of granite. And so melting can and should occur during slip events. And then this plot from Detour 2006 shows the effect of normal stress versus the shear stress and the familiar Byerlee frictional strength. However, we see that natural data and the experimental data fall well below this Byerlee strength. And so there's some weakening occurring on the interface by these frictional mechanisms, and melt provides a lubrication mechanism to explain this weakening. And so we have, some kind of lubrication mechanisms along these glowing red curves, and how that's different from this gold area, the Byerlee friction. And then this paper from Chen 2017 looks at the evolution of the interface in the presence of melt with continuous slip. So this isn't really stick slip, it's just you're continuously moving the samples past each other and generating melt. And many other people do these with a variety of rock types. And they started to see this characteristic evolution of the interface, of the sliding strength of the interface. And they've categorized this as sort of this stage one, where you have comminution and powder lubrication, and the generation of these fine-grained materials increases the surface area of the interface, and it allows melting to actually occur at lower temperatures. And then as you have melt occurring, you start to get into maybe a viscous breaking phase, a dynamic strengthening of the interface, and then ultimately towards full melt lubrication. But like I said, this is with continuous sliding, and it's interesting to think about with the E-core apparatus, where you can have these indefinite events with an indefinite stick slip, and we can generate melt. How does the static strength of the interface change, and as well as the sliding strength? And as far as static strength, there's the idea of melt welding, where this diagram is simply showing that the strength of the interface is increased when you have melt forming and later cooling and bonding the opposing slip surfaces together. So melt welding can increase the static strength of the interface, and may be expanded into more like regional problems, like thinking about where the next earthquake will be, where the next earthquake location along the fault strand, and where the strain energy is going to be released along a fault. Like I said, we used polymethyl methacrylate here, and you might ask why PMMA. And so PMMA is commonly called plexiglass or acrylic glass, and it's widely available and widely used. It's used in a variety of applications. It's used for things like submarine windows. It's used for glass in aquariums, art, the beauty world, everything. And that's because it's really easy to fabricate, machine, and thermoform. And this is because it has a low melting point and low strength. And that's ideal for our experiments as well. We can easily melt the plexiglass, and it's optically transparent, meaning that we can view the evolution of the interface as the event's evolving. And PMMA has been used extensively in friction experiments. Here's an example from McClaskey and Glazer, 2011. And they found that PMMA strongly resembles crustal rocks, including its acoustic emissions and how the strength evolves. And this goes back to Dieterich and Kilgore, where you see they experimented with a variety of materials: granite, soda-lime glass, and acrylic glass. And in this rate, sort of like rate and state sense, where they're changing the slip velocities, you can see that the shape of the curve, the frictional evolution in acrylic glass strongly resembles that of granite. And it behaves very similarly to granite as far as how the strength evolves. And in a thermal framework, we can relate PMMA to granite through something called the homologous temperature, which is simply the ambient temperature over the melting temperature. That of PMMA is 0.7. It's also 0.7 in granite. So this is assuming a specific thermal gradient and some melting point. But nonetheless, it's in the same ballpark as PMMA, kind of testifying to the similarity in its properties. So here's here's our actual sample. It's two pieces, and I drew an outline just to show those two pieces more clearly. We have our upper cylinder, which is slightly thinner than the lower cylinder. And the upper cylinder has an inner hole that's drilled so we can thread a thermocouple in, and then an outer radius. And these are, that outer radius is about 20 millimeters. Some other key points is that its melting point is between 130 and 160 C, so really attainable at standard temperature and pressure conditions. We're using a normal load of 3.5 megapascal, and then we're changing the loading rate. And this is, we're going to think about this methodology more, but changing the loading rate from initial of 0.15 megapascal per second to a higher loading rate later of 1.5 to 1.6. We prepare these surfaces just by cutting them and then making them uniform with a lathe. And then we polish them for 1 minute with increasingly finer grit silicon carbide paper, and then ultimately using water to create a slurry that can create a really nice polish on the interface. So we have a pristine interface to start with, and then we clean that interface off with some alcohol. Okay, back to this experiment with PMMA and the experiment we're going to discuss for the rest of this talk, essentially. So we've divided the evolution of this experiment into 4 different phases. The first phase occurs when we have this lower loading rate of 0.15 megapascal per second. And the second phase is when we have the higher loading rate, and that follows into phases C and D, the third and fourth phases. So we'll talk about those one by one and step through those. But first, let's get calibrated on some of these different variables we're talking about. So zooming into a stick slip event from phase C, these are the terms that I'm going to be using. So in the light gray, we have the time versus friction evolution, and it's growing here. In this scale, it's harder to see, but it reaches a peak static strength or peak frictional strength, and then it drops suddenly across some critical slip distance, and then starts sliding at this residual friction or sliding friction or dynamic friction. Those may all be used interchangeably. So yeah, sorry for that. But the slip velocity, what we're defining as the slip velocity, is this velocity that's happening at the same time as that sliding. So it's the velocity during slip simply. So jumping into phase A.
Yeah, I'm sorry. Can I ask you two short questions? The first question is that your rotary experiments, you are applying the slip velocity, or you are just applying the load? So is load controlled or velocity controlled?
Thanks for the question. That's an important clarification. Yeah. So we're controlling the velocity of the motor. And by controlling that, we're controlling the rate in which the spring is loading. And the velocity of slip is responding to the rate which that spring is loading. So all we're controlling is the motor.
It is a load control.
Exactly, yeah.
Okay. And the second question is that when you, in this picture, am I wrong that you reach the peak slip velocity when you already are reached the minimum friction?
Sorry, repeat that, the first few words.
Do I interpret well this picture here, interpreting that you reach the peak in slip rate when the dynamic weakening is almost complete?
Yeah, that's what we're seeing in our experiments. Yeah.
Okay, yeah. Thanks.
Of course, thank you.
Sorry, it's Chris. I just wanted to further clarify that point. So the feedback that you control the loading rate,
right?
And the feedback that you have on that is a servo controlled system, so that you really try to control the load, because actually it seems like you probably just control the rate, I suppose.
Oh, right. Yeah. So yeah, thanks again for this clarification. We're just controlling the rate, and we're saying that the slip velocity, and when slip occurs, is, and we'll get in, well, I'll kind of expand on this more, but it's a function of the relationship between the energy flux that's provided from loading the spring to the interface, and then how you dissipate that energy flux after slip. So we're only controlling the rate of loading, and we're calling it energy control because we're controlling how that spring is loading, and thus the rate of change of energy that's being accumulated in the spring.
Yeah, it makes sense.
And, yeah.
But this means, Ethan, this means that your slip velocity is not directly controlled by the rate of displacement, because you measure it for the energy or not? So do you don't?
So we're measuring, we're calculating the energy from the slip velocity is part of how we're calculating the power density or the energy dissipated by friction. So yeah, so that's
okay. Because I need to understand if you have some smearing in your calculation. Okay, thanks.
yeah, no problem. Thank you. Of course. Yeah, this is a good point to move on to. So kind of entering phase A. So this is our first phase at the lower loading rate. I'm just calling this dry friction because it's without melt. And we see relative to the other phases, small slip displacements, a lower friction drop, and the energy flux is low relative to those other the other phases. The period is 3.3 to 6.4 seconds, and that becomes important when we increase the loading rate. And then in acoustic emissions, we see the small spike at this scale accompanying the slip event. So here's some snapshots from those 960 frame per second recordings. We have before the event, shortly after rupture, and then after the event. And we're going to look at these quite a bit as we move through the talk. So the key for these interpretations is the dark transparent color that we see pretty much everywhere here is pristine slipping zone. It's basically the air in between the interface. The light can pass through very easily. And then the semi-opaque spots, which we don't see here, but we'll see moving forward, are melt patches and layers because the PMMA has broken down and reformed, and it starts to scatter the light as it passes through because the atomic structure is effectively changed. And the bright and transparent features, which we do see here, are granular PMMA or in later cases solidified melts. And in these experiments, like I said, we see a relatively pristine surface with some groove that's kind of being formed maybe from a small class, plowing that groove into the interface, creating maybe some powder. We don't have, the pictures aren't high enough resolution to see any powder or anything. But we do have SEM images of the interface. And what we see on the interface are these brittle deformation features, these kind of striations and fault steps that you would see at like at an outcrop. And so here's kind of, my mouse isn't responding super quickly, but here's these striations here. Here's like some examples of what we're saying these fault steps are. And like I said, this is kind of just taking a map view on the interface. Then we increase
Adam, so sorry. Yeah. My last question, I promise
of course.
you. So
ask as many as you want.
Because I want to understand better the experimental results. So in the previous slide, when you saw this temporal evolution with the 4 phases, where the first round of the fault occurs. So which is the first when the first torsion is concluded here, or these are multiple rounds?
These are so like the start of the experiments back here, and you'd see the shear stress increasing, and then you would start the experiment. So there's like some initial increase which we've cut off here because there's all this other noise from us putting the barbell plates and stuff on top. So this is the start of the experiment, and these are individual stick slip events. And then this is kind of evolving.
How many rounds the machine did in this 200 seconds? So multiple.
Yeah, multiple. Yeah, many rounds.
So this means, that you have a sort of stationary properties, because when you in a rotary, you do not preserve the initial condition of the interface. The interface are always perturbed. This means that you have a sort of steady state interface features that you maintain over multiple rotary experiments.
Exactly. So over multiple events, you have relatively regular behavior until we change the loading rate. And we would expect this to maybe occur. Okay. We haven't experimented through this, but this supposedly could occur indefinitely, that you would the interface reaches some kind of steady state effectively, and then the amplitude or the peak friction doesn't increase. Everything remains relatively uniform.
Thanks. Now I understood, and I will be quiet. Thank you.
Thank you. Yeah, so we were just jumping into the phase B. So this is after we increased the loading rate. And with the new loading rate, obviously the slope of the shear stress curve is going to increase because we're loading more rapidly. With the friction drop, we have slightly higher displacement, slightly more energy flux to the surface. There's a little more action and more information in the acoustic emissions spectrum here. And importantly, the period decreases. So we really increase the frequency of events, and this leads towards a building of the fault temperature, because between events, there's less time for the heat to dissipate. And so there's this memory of the heat from the previous event, and you're kind of building onto that. And we see that here from the transition point, kind of the end of this phase, the exponential increase in temperature because you're building and you have these very rapid events without enough time for heat to dissipate. And in these frames that we have below, we see that we're starting to form melt in this semi-opaque color, and there's some PMMA gouge or powder sort of entrained in this melt and then later cooled in this melt. But because of the melting, because of the melting, and the starting of bonding the interface, each event gets bigger, and thus you create more energy. You release more energy in each event. You have more melting and more bonding, and the temperature continues to go up. And this is what we're calling this kind of temperature and shear stress runaway, where everything very rapidly increases and becomes very large events because of this welding effect. And we enter phase C, and like I said, we mark phase C at the inflection in this curve here, where we have this change in the shear stress. It's sort of between the change. You see there's some larger events here, but really once you've established these larger events, and the temperature has reached a new kind of trend, it's increasing linearly now from here. In this phase, we see way more interesting things, just because the events are larger, so you really just have kind of better resolution too. But we see a foreshock that's happening before the event. In the AE, that foreshock seems to kick off some different behavior in the AE signal. Then with the slip event, we have more displacement here between 2 and 3 centimeters. We see the reversal of the displacement, so it's turning and then bouncing back because from the inertia of the event. And then we see the much higher energy flux associated with each event. The temperature spike is significantly higher. Using that formula that I showed before from Karlslaw and Jaeger, it can be up to 460 degrees Celsius with each event. And so and that's very short amount of time that you reach those temperatures, but you're melting a lot more, and especially at the tips and at the micro scale, at the disparity tips and things like that. So it's really kicking off this feedback, and events are getting much larger. And in phase C, we can see this circular patch of welded pseudotachyllite before the event, and then after rupture, we can image the patchy melt kind of forming and then coalescing into a continuous ring, leading towards later arrest. In the SEM, we have some images of the interface between the two. This is taken at the edge of the sample, and we see these kind of globular melt forms connecting the two samples. And then I ignore these. I accidentally left them in here, but I'm just talking about stretched melt filaments here. Apologies for that, but these globular kind of forms have been stretched out by the displacement and thinned and elongated, and that's what we're seeing, these kind of elongate melt filaments on the melt patch. And this is kind of like, yeah.
So can you tell us what the slip direction is here? It looks like the radius of curvature is changing, so it's not exactly following the striations.
So the slip direction, let me just make sure I get this right. I should have put this on here because it's always kind of a brain bender when I start to think about it. So we're loading this way. It should be, Okay, so it should be this, it should be from right to left if I don't have this mixed up. Yes, apologies for not putting that on there.
But it looks like the radius of curvature of these striations is not spatially uniform. So it's they're not all arc. So some of this, the structure is mostly parallel to the slip direction, but not exactly.
Yeah, and that might be maybe because you have like kind of this more chunky patch that could be like a discontinuity in the flow and like kind of disturbing the stretching of these filaments. I mean, I think that this gets quite complicated when you're starting to interpret these stretched out filaments. But that's a really interesting point.
And the slip rate is less as you move in, so presumably the temperature is lower toward the interior.
Yeah. You would think so, yes. And I mean, some of the temperature is like going to be, it sort of is conducted pretty rapidly throughout the material. But yeah, that initial spike is going to be obviously the maximum at the maximum outer radius, and then less in the inside. And then like thinking about those grooves that formed, those are going to form like, if you will, basins for the melt to kind of fill. And any fractures are going to be, you're going to, like in that picture, for that illustration from Julio, any fractures are going to have that melt injected into there because the surface is highly pressurized.
And PMMA expands when it melts, or do you know what is there a volume change?
I don't have a number for that, but yes, yeah, it would expand. So
because it's conceivable that stuff is getting squirted, you know, maybe you'd see this out the perimeter or
yeah. Just wait 1 second and I'll show you a really cool video.
All right, I'll shut up.
Yeah, you took away the mozzarella cheese. I'm sorry, it's okay. But yeah, I was saying like spreading mozzarella cheese like this. But okay, so jumping forward. So yeah, we have the kind of the SEM images. Then we enter a phase of stable sliding. And I'll show that video I was mentioning, Mark, in just a second. So entering this phase, we have no change in the shear stress. The displacement's obviously linear because there's no stick slip. The energy flux is constant. It's zero because you're not accumulating energy in the spring. We see shortly after the onset of stick slip, the formation of this melt patch. It starts to thicken and thicken more, forming this brighter red color as the experiment goes forward. And then here's looking at this transition in itself. So here's just the key for the interpretation. So we have the last event. We see the melt patch kind of changing and fluctuating. We see another kind of smaller event, and then it starts to slide. And so there we have it, just sliding, and the melt is going to continue growing from there. And then here's that video I was talking about. We can see this is a time lapse, and then we'll in the plot below I have the vertical displacement and the shear stress. The sample is shortening significantly, and we see the extrusion of that melt out of the interface. I want to show that again. There's a lot of media in this presentation, so it's a little slow. Okay, yeah. So and it's cool too. You can see this kind of the ejection of powders at first, and those powders are forming kind of like material that melt can incorporate and kind of include into the melt. So it's like cool to think about how the powders are melting and easier to melt and form kind of fuel for the melt in a way. So kind of ending this part, thinking about the patterns of that have been summarized in Chen 2017, where you go from the sliding strength of the interface, from this like powder lubrication phase to formation of melt and viscous breaking, and then later full melt lubrication. What does this look like when you have these thick slip events occurring? And as we change to the transitional phase and we start to have melt production, we have a slight increase in the dynamic strength, but we also have this static strengthening, as we showed from the work of Proctor and Lochner, where you're bonding the interface and you're increasing the static strength. And then this is leading to that feedback that I was mentioning, ultimately ending in full strength breakdown and stable sliding. This leads into the next phase, specifically this welding, melt lubrication, and viscous braking. And so this takes us nicely into this part on monitoring the coseismic strengthening and weakening through these energy fluxes and slip velocity and how they relate to acoustic emissions. So let's go with that, and we'll start with another very introductory diagram showing the graphical representation of the energy budget during an earthquake. Here we have slip distance against shear stress, and this is probably very familiar to many, but that frictional energy part down there is what we're interested in. So the total budget is made up of that frictional energy and the fracture energy and the radiated energy. But studies show that frictional energy is greater than 70%, maybe as much as 90% of the total energy budget. And then Retch's 2019 used this to say that this is where this energy flux and relationship with the dissipation and the interface is coming from. Is they say that it continues, slip will continue if the energy flux, so the rate of energy supplied to the interface is greater than what can be dissipated by frictional processes. And like fuel in a car, the energy flux is the gas, and the power density is consuming that. And energy flux in crustal blocks can control their slip style. So it could be slow slip or fast slip, and also the coseismic slip, the velocity. And looking at the energy flux and power density, so this is just like a simple equation to show what we're talking about. We're talking about the rate of change of both of these quantities. It's highlighted in red here, the power density. I know it's a little confusing with the EF and energy flux, but that's the power density. And so the energy flux is the amount of supplied energy you have, and that power density is what's mainly dissipating that energy over the area. So let's get into some phase C data. We're zooming in on one of these phase C events. And so it's shown in Rice 2006 and other places that flash weakening or flash melting occurs over a critical thermal slip distance, which is related to the critical weakening distance, that's D sub C, that may be familiar to many, when the velocity exceeds the critical weakening velocity. And the formula for that weakening velocity is shown here, also coming from Rice. And then here's all the numbers that we use to calculate that weakening velocity. The thermal weakening distance we used from the measure disparity size, as well as is used in the rate and state fit, so it fits pretty well. And then the shear stress at the disparity tips is around 10% of the shear modulus, and that's coming from Diederich and Kilgore. Maybe the reference is on a different animation. So the slip velocity, the weakening velocity we get is around 0.02, 0.07 meters per second, and that's glowing here now red in these horizontal dashed lines. And so, as it's stated, when the flash weakening occurs over this critical thermal slip distance, and then the interface enters a weakened state when you exceed this critical slip velocity up until you end the event and you reach, you start to cool and bond. So this is when you're in that thermally weakened state. Okay, changing it up a bit here too to talk about kind of the next steps, like kind of thinking more about the energy fluxes, right? So as we said, slip continues if the power density dissipated by friction is greater than the energy flux provided from the spring. Again, the energy flux is calculated from the storing of spring potential energy and that how it's supplied to the interface. And so if the spring is coiling, the energy flux is negative in terms of our sign convention here, just because it's accumulating energy, and it's positive when it's releasing. So when you see it go up, the energy flux is the spring is uncoiling and energy is being supplied to the interface rapidly. And then the power density is simply the shear stress, the sliding shear stress times the slip velocity. So this is kind of the power the power over the area that's dissipated by friction. Okay, so when these cross, then you would lead to slip deceleration and viscous strengthening. And so we see what was stated by Retch is that when you change over, you start to enter this arrest phase, and things start to come to an end, and you start to slow down, and then ultimately you get to arrest. And I like to think about this like a burnout in a car. So let's say you're revving the engine and you have the clutch fully depressed, and then you drop the clutch very rapidly. The torque supplied to the wheels is going to be more than the interface between the tires and the pavement can handle. And so the tire is going to just spin until the energy that's dissipated by friction can exceed that's supplied by the motor to the axle, and the car will speed away. And so the earthquake really acts in this way. It's sliding, and then you start to create a melt patch that thickens enough that you can slow the event. And so here we have that shown in high frame rate video. So we start with the radial contraction of this PST patch. This is super cool, and I'll kind of highlight some of that later. But then the onset of melt weakening, the formation of the melt patch, we see a growing and thickening on the interface. And then as that grows and thickens, we're in this lubricated state now, we see the onset of viscous strengthening and slip deceleration, and things start to slow down. Okay. So we've kind of pinned down these different phases and the relationship with energy flux. And now let's look at the acoustic emissions. So this first little bit is kind of a zoom on the
Adam, sorry, before that you move to the acoustic emission. So, but therefore, when you have the individual release, do you really observe a constant residual stress?
Let's go back to here, because we have the stress there. Yeah, so it's constant after the critical slip distance, or pretty much. So if you could bracket it here and here, this is where the slip is roughly constant. And then it slightly increases. And then if you, at a different scale, you could see this much better. But the strength, it rapidly goes up here. So once you enter the arrest phase, you have that like kind of classic curve with kind of a rate and state fit, where you have the decrease and then later strengthening with continued displacement.
Yeah, and during your phase C, you have multiple of these events, no? Because during the entire ramp up to the peak.
For sure, yeah. This is from the middle of phase C. So this is after melt has been generated, and this kind of melt strength feedback is going on. Yeah,
that is interesting. Okay, thanks.
Mm-hmm. Okay, we're getting there. Let's see. Yeah. Okay. So we're looking at the acoustics emissions data. We've pinned down these different things. And then, so here's the AE spectrum. We have kind of this burst associated with the onset of unstable slip, and then some changes in the spectrum, and then this kind of burst again as you get into this strengthening phase. Looking at a spectrogram from this time series, we see some precursory signals kind of buried in here, and then you have the burst in AE power associated with the rupture, and then it's silence as the melt is formed, and that melt is attenuating the sound waves that are being emitted from the interface. There's this question mark period where we see a flash in power, and then we have the slip deceleration, viscous strengthening. So we're uncertain about this and what this actually represents. Maybe another mechanism kind of coming into play, maybe just kind of the gradual slowing of the interface, the gradual increase in melt, and therefore leading into that viscous strengthening. But using an equation from Nielsen 2008, we can think about the time needed to form a continuous melt patch, and that's shown in this light gray here. So the melt is forming here, and then you have this continuous melt patch within this window of silent acoustic emissions. So the key takeaways here are that following retches, the high velocity slip is maintained when the energy flux equals or exceeds the power density. When this is overcome, you enter a viscous breaking phase. And this corresponds, this viscous braking phase, to a roughly 50 decibel per hertz increase in power in this band that we were looking at. The strengthening and weakening mechanisms seem to have peculiar or characteristic acoustic emissions. And we think that, maybe they have an equivalent signal in nature with improved instrumentation. Once we kind of get closer and rid of the noise, maybe we can start to see these things. I don't know. And then after final arrest, the interface drops below the glass transition and the melt solidifies into a pseudotactylite and welds the fault. So if you want the volume up, we can hear everything happening. I've kind of made an audio of this, so we can hear the precursory things, the kind of cracking, fractures forming, and then I don't know if I'm sharing my audio. Let me try this again. Here we go. Let's try this. Sorry about that. Okay. Yeah, so I bugged it out here. We're just going to skip past that if it doesn't go. Sorry about that. Yeah, all right. So sorry you didn't get to hear it. If you want to sometime, I'm happy to send the file to you. So in summary, and like kind of thinking about natural applications, these experiments support the occurrence of frictional melt lubrication associated with seismic slip, providing insight into the interface evolution. They support the strengthening mechanism leading as a result of the formation of glass and the welding of the interface. This may hinder reactivation of the fault. In nature, pseudotactylite formation may occur in the lower and upper mantle in this kind of ductile field. And so there's the question is, how do you generate shear instabilities within this field? But we have intermediate depth earthquakes. So one explanation is that the strain is localized around a discontinuity in the body, and pseudotactylite might provide a small scale strength variation in the body. So this is like thinking about how some of these things can be applied. And then Kendrick 2014, instead, in also a very hot setting, the Mount St. Helens volcano, used high velocity rotary shear to investigate the ascent of magmatic plugs. They used acoustic emission sensors, and they saw that, and people have described this kind of drumbeat of acoustic emissions, suggesting that the ascent is thick slip along these faults bounding the plug. And our phase C events support the idea that frictional melts and pseudotactylites assist in nucleating those instabilities and also in arresting the slip of those instabilities at these higher homologous temperatures. Then I just have a quick picture from a pseudotactylite vein I found in a cobble in Colombia. I'm headed to Colombia tomorrow, so I thought that was kind of appropriate. It's a very underwhelming example, but the only picture of pseudotactylite I actually have taken in the field. And then this is just where I'll end these next two kind of slides, just future directions, thinking about rupture propagation. So what we're looking at here is the fault interface. It's loading. Yeah, so what we're looking at here is the fault interface. And I see that by sharing the computer sound, that was a mistake. Okay. Okay, so here we go. Yeah, so the melt patch, like checking out this melt patch, we see the patch that's formed, and then we'll start to see it shrink concentrically as you lead towards rupture. So we're watching it. It's moving very slowly, almost imperceptibly, and then it rapidly shrinks, and we see that melt forming with the event. And so what we could do here, for example, is we can look at that. We can segment that image, and then we can actually measure how the area of the interface changes through time leading up to the event. And so that's exactly what we're seeing here. On top, white is the melt patch, black is the pristine interface, or things that aren't the melt patch, and we'll see the shrinking, and we can see it in the curve of that melt patch, and then final breaking. Here's some plots from different events. The order just means different events, kind of a confusing term, but yeah, it's just meanings. Yellow and orange and purple and green are separate events. And we see, yeah, the radial shrinking of the melt patch, and pairing that with acoustic emissions. There seem to be, again, characteristic acoustic emissions associated with these precursory phases of rupture propagation, where we have this like very slow propagation, a much faster propagation, and a change in the AE spectrum. The white here is showing the displacement, which also changes in its behavior. The rate of change also changes as you change as the AE spectrum changes, and then ultimately you have the event. So this is kind of just like a teaser for the work that can be done in the future. And with that, sorry for going a bit long. And I thank you for the questions during the talk for clarification. Just gonna, acknowledge the group, of course, Nicola for helping me out with this, for introducing me to the machine, and for like making what I think is a really pretty interesting, some pretty interesting results. And then everyone else that worked on this, Catherine Rieger, who did her master's on these experiments, and then Phil, who did SEM imaging, Benoit, who co-designed, conceptualized, constructed the machine, and helped with SEM imaging. And then my co-supervisors, Claudio and Torsten. So with that, yeah, that's all I have for you, and thank you for your attention.
Fabulous, Ethan. Thanks a lot. I'll invite everybody to unmute, join me, and yeah, thank you, Ethan. Fabulous talk. A lot of interesting stuff. Okay, so simplest thing for us to do is to use the reaction button at the bottom of your screen, and raise your hand. Will put us in some kind of order to ask questions and have a discussion. And thank you, Paul Johnson, for getting us started.
Really enjoyed the talk.
Thanks,
Ethan. Thanks very much. And you managed to stay on track despite all the questions in the middle of the presentations. I had a question about whether or not we were looking at something real or artifact. When you showed the full experiment, shear stress,
Yeah.
et cetera, if we could go
Yeah,
back to that in the different phases.
Yeah. Oh, the full
Yeah,
experiment.
yeah.
Yeah, let me zoom over.
Yeah, the full experiment. Yeah.
Race car. My computer is very unhappy with the amount of videos and animations I put in there. All right, here we go. Let's go to when it's like, when we have a good view of it. Here we go. Okay.
Okay, so when you zoom in on these, it was a couple of slides hence.
Yeah.
The shear stress oscillates post failure.
Yeah.
And is right there, phase A, upper left-hand corner. Here's a great example of that. Is that an artifact of the device and the design, or is that something real?
I think you could call it an artifact. It holds information physically. It's like the sample assembly is spinning so fast that this is like the recoil response, and so it stops, and then the machine recoils, and so we actually see in the displacement curve here. Let's go to the phase C event. Yeah, in the phase C event here, we see that up here, we see that recoil. So the whole thing is reversing because it's overshot, essentially, the amount of rotation.
Right, okay. Yeah, thanks for the clarification. I mean, I think, every device has this kind of effect, I guess. And, you might very well expect this in Earth as well, depending on the characteristics of the fault. So,
Yeah.
Very cool.
Thanks.
Great. Thank you for the presentation. That's all for now, Ethan.